Hello, and welcome to the MEaSURE project. This is an adaptation of Eratosthenes' method for measuring the Earth that is intended to be accessible to students worldwide. The measurements are taken on either the spring or fall equinox at solar noon, which is very likely to occur in the middle of a school day, which makes this a perfect school project. But this experiment could also be performed by anyone with an interest in math and science and who wants to participate. Please look for links to a data entry form and other resources. The following description of the project is modeled after a lab report and contains results for the first time this experiment was performed. Astronomy and geometry have been studied since ancient times. Over the course of many years, evidence appeared to suggest that the Earth was round, even if it might appear flat to a naive observer. For example, ever since we've been building ships tall enough, we've seen them disappear bottom first over the horizon, as if they're going over a hill. When they approach, they appear top first. Or you see how the Earth casts a circular shadow over the moon during a lunar eclipse. However, knowing that the Earth is round is not the same as knowing how big the Earth is. Almost 2,300 years ago, a Greek mathematician named Eratosthenes devised a way to measure the size of the Earth. A city in Egypt happens to fall right on the Tropic of Cancer, which means the sun is directly overhead there at noon on the summer solstice. This is important for two reasons. First, the summer solstice is an astronomically significant day, so you could know with certainty that two observations are being made under the same astronomical conditions, even if they're made years apart. Second, it simplifies the geometry. If the sun is directly overhead, then the sunbeam is collinear with the Earth's diameter. If you measure the sun's zenith angle at another location at the same longitude on the same day, then you've measured the latitude between those two locations. But knowing the angle is only part of the puzzle. You also need to know the length of the arc subtended by the angle. Eratosthenes' second measurement was made around 800 kilometers away, where the shadow made an angle of 7.2 degrees. These values give this proportion. Now, I'm at a disadvantage. I don't live anywhere near the tropics, plus I'm a teacher and my school isn't in session on the summer solstice. However, I do have another astronomically significant day, two of them in fact, that do happen during the school year, and some math that was developed after the time of Eratosthenes that should make it possible to do this anywhere in the northern or southern hemisphere. Everyone who participates needs to measure their solar zenith angle at the time of solar noon on an equinox, either spring or fall. You see, on the equinox, the sun is directly over the equator, and as a result, the solar zenith angle will be equal to your latitude. Here's your experimental setup. First, you need to have a vertically standing meter stick to cast a shadow. Next, you'll need a horizontally laying meter stick to measure the shadow. You need to have this meter stick pointing towards the geographic pole, which means if you're using a magnetic compass, you need to account for magnetic declination. Solar noon occurs when the shadow reaches its minimum length. Note, this noon isn't the same as 12 p.m. Solar noon refers to the moment when the sun is at its highest point in the sky, which casts the shortest shadow. In the northern hemisphere, the sun will be directly south of you, which means your shadow will be pointing north. But in the southern hemisphere, the sun will be directly north of you, which means your shadow will be pointing south. If you're on the equator, you won't get a shadow at all. The solar zenith angle is the inverse tangent of the length of the shadow divided by the height of whatever is casting the shadow. On the equinox, the solar zenith angle at solar noon will be equal to the observer's latitude. Now, latitude is easy to measure because you only need to determine the angle to astronomical landmarks like the sun or certain stars in the night sky. However, since the Earth is rotating, longitude is much harder to measure. Astronomical landmarks constantly move from east to west across the sky, so you would need to know exactly what time it is when taking your measurements. That's why longitude couldn't be measured reliably before the development of precise mechanical clocks in the 1700s. When each observer makes their observations at solar noon, they must also note the time. Since the Earth rotates a full 360 degrees in 24 hours, we can work out the fraction of a full rotation based on the time interval between each location's solar noon. The longitude angle between each observer is given by this formula. So, for any two observers, you should have two latitudes and two times, which lets you calculate the longitude between locations. This particular experiment was carried out for the first time on the spring equinox of March 2025. Two schools on either side of the Atlantic Ocean, one in Germany and the other in the United States, took measurements which I will present to you now. In Germany, the shadows of three 150-centimeter rulers were measured, giving a latitude of about 48.5 degrees, give or take half a degree. In the United States, the shadows of 5 individual meter sticks were measured, giving a latitude of almost 39 degrees, give or take about a quarter of a degree. In Germany, solar noon was observed at 12:31 p.m. local time, while in the United States, solar noon was observed at 1:10 p.m. Between different time zones and daylight savings time, that works out to a 5-hour, 21-minute rotation of the Earth, which is only about 22% of a full day, which means it's about 22% of a full 360-degree rotation, so the calculated angle of longitude between the observers is 80 degrees and 15 minutes. This is almost enough to calculate the Earth, but first we need to do a little trigonometry. Take the latitude measurement. If we look at a cross-section of the Earth, then we see that your latitude is complementary to this angle made with the Earth's axis. Now we have a side of the triangle laying in a plane tangent to the North Pole. We can do this with both locations. Now that we have two segments in a plane tangent to the North Pole, we find that the angle between them is the longitude between the observers. We can also construct a third segment to complete a triangle, which is significant because that also completes a second triangle which contains a special angle, the one that subtends the great circle arc that is the shortest route between the two observers. A couple applications of the law of cosines and a bunch of algebra later, we arrive at this equation. If you'd like to see a full derivation, check this timestamp. Now, having this angle is crucial because this is the angle that Eratosthenes used to measure the Earth. Ours was just a little harder to get, so I think it's only fair that we take the easy road for a change and just look up the distance online. According to Google Earth, these two measurements were taken 6,540 kilometers apart. That distance is an arc of the Earth's circumference subtended by this angle, so if you work it out, you get a radius of 6,672.5 kilometers. That's less than a 5% error. This experiment was designed so that it would be accessible to anyone with basic lab equipment during the school day, during the school year. Student involvement can be anywhere from only taking the measurements, which anyone who can read a ruler can do, to setting up the experimental apparatus, calculating the angles, and even deriving the formulas needed for calculation. The experimental setup can be as simple as 2 meter sticks and a compass, or incorporate any number of cleverly engineered improvements. It can be done competitively, like who in our school can measure our latitude and longitude the best, but also must be done collaboratively, since you need multiple observation locations in order for it to work. In other words, teachers could guide their students through all kinds of variations of this project geared toward their students' abilities and still fully participate. Every year, do it all over again with a new group of students. Make it an extra credit assignment so you don't have to deal with it. Anyone can do this. Homeschoolers, astronomy nerds, anyone with a couple rulers and a compass. Having done this experiment already, there are a few things that are worth mentioning as part of this discussion, so here they are for your consideration. First, diffraction and the angular size of the sun cause the boundary of the shadow to have a poorly defined edge. This makes it difficult to get a precise measurement of the shadow's length, though a meter stick shadow can still be estimated to the nearest centimeter. It also makes it difficult to tell exactly when the edges of the shadow fall along the north-pointing meter stick. This would be a great place for some clever engineering to improve the precision of the shadow measurement or determining when exactly solar noon happens. Speaking of determining when solar noon happens, because the magnetic poles are not the same as the geographic poles, it's necessary to take magnetic declination into account when using a magnetic compass. Failure to do so will affect both longitude and latitude calculations. It's also apparent that magnetic materials cause interference with magnetic compasses. This was most evident with the steel ring stands that were used to hold the meter sticks, but placing the compasses on the ground also seemed to cause errors. Maybe this is due to buried metal like rebar, plumbing, or electrical conduits. Just be sure to account for all magnetic interference if using a compass. And don't forget that solar noon also happens when the shadow is shortest, so it is possible to do this experiment without a compass as long as you monitor the shadow's length. The measurements in the United States displayed a uniform shift to the south, about 1 degree compared to expectation. Now this can't be due to timing, since an early or late measurement would have produced a longer shadow, which corresponds to further north. It is possible that the ground was tilted slightly towards the south, which shortened the shadows. It would be a good idea to verify that the surface you're working on is level before making your measurements. Unsurprisingly, the historically difficult longitude measurement is still a challenge. Because the Earth rotates at 15 degrees per hour, a 5-degree difference from expectation correlates to a 20-minute discrepancy in the measurement. You could have an east-west measurement off by hundreds of kilometers. This may be responsible for most of the error in this experiment. If we underestimate the longitude difference, that would lead us to assume a larger Earth and an overestimation of the radius. Okay, using Google Earth to measure distance may seem like a bit of a cheat. In the original Eratosthenes experiment, the distance had to be physically measured. Measuring shadows might be something a group of students can do during a school day, but measuring the distance across an ocean doesn't fit a school schedule or budget. Ironically, this makes this experiment into a latitude and longitude confirmation, since it compares the distance that corresponds to your measurements to the one that corresponds to your GPS. But this isn't a real problem because experiments are performed all the time based on values that are looked up rather than independently verified. But these distances can be verified with a road trip. So having acknowledged the limitations of this experiment, a bunch of consistent results with a few verified distances is enough to support the underlying assumption of a spherical Earth. The formulas are for spheres. Any other interpretation of the data would require different equations based on different geometry that give a different consistent result, which also matches confirmed distances. Speaking of the formulas, the spherical law of cosines can be derived as follows. A straight path on a spherical surface follows a great circle, which is a circle with the same diameter as the sphere. That means that the sides of a spherical triangle are circular arcs, not line segments. The vertices of our spherical triangle are a pole and our 2 observation locations. The sides connecting each observation location to the pole are the complements of their latitudes. Finally, you can also construct this right triangle within the cross-section of the sphere. For the sake of convention, let the W subscript be for an observer to the west and the E subscript refer to an observer to the east. Neither observer is more important, and it wouldn't be right for one of them to be observer 1 or A or something that implies primacy. The angle between these sides is the longitude between observers, which will be labeled L. 2 of these sides lay in a plane tangent to the pole, and the law of cosines gives an expression for the remaining side. A similar construction can be made for the plane that contains the great circle connecting the observers. That's the same segment, but this time it's opposite the angle that subtends the arc that connects the observers. Let's call that angle D. If you apply the law of cosines to this triangle, you get this expression for the third side. So, from each triangle, we have 2 expressions for the same side. Since these are equal, we have this equation to simplify. Square both sides. Subtract everything from the left. These terms can both be simplified with a Pythagorean identity. Divide both sides by 2. Now solve for cosine of D. Add secant phi W, secant phi E, cosine D to both sides. Divide both sides by secant phi W, secant phi E, and simplify. This gives us an expression for the spherical law of cosines with the notation in this experiment. We now have 2 expressions for the same distance. a distance measurement from Google Earth, and the circular arc subtended by angle D. Substitute measured values and you have a value for the radius of Earth. Compare it to the established mean value of 6,370 kilometers. Okay, the last thing that I need to discuss is the information that you will need to provide in order to participate and what I'll be using that data for. First, please use Google Earth or a similar GPS service to find the precise geographical coordinates of where you made your observation. Please make that precise to the minute or 60th of a degree. This is necessary to calculate distance between observers, but it's also a form of data validation because it will help us to diagnose error if your solar azimuth angle is substantially different from your latitude. Second, please note the time of solar noon because we need that to calculate longitude between observers. Also, while it's not strictly necessary that the observation happens on the equinox, it must happen very close to the equinox. So just to make sure that we can account for all forms of error, please note the date that the observations were made. The remaining information is completely optional for participants to provide. Because this is a collaborative experiment, I'd like you to be able to share the global reach of this project by just sharing a little bit about whether you're from an academic institution or professional or just an interested amateur. I'd also like to give you an opportunity to share your experience with the experiment. What did you try? What went right? What went wrong? Anything that you would put in the discussion section of a lab report, I would love for you to include it. Now, this data is publicly sourced, and so I would also like to make it publicly available. This doesn't belong to me, it belongs to all of you. That means your geographic and astronomical data, your latitude and longitude, solar azimuth angle, time and date of solar noon, will all be publicly available, anonymously, completely unattached to any identifying or demographic information. As for the optional information, I'd like to be able to share your messages with the broader community participating in this experiment, and that means that any comments or innovations or suggestions or anything else that you'd like to submit, I'd like to be able to share with everyone. That can be as anonymous as you choose, and I won't associate it with the geographical coordinates of where your measurement was taken. Thank you so much for considering participating in this experiment. I'm looking forward to the next equinox.